Hello everyone. For week 3, we're diving into chapter 31, which is a pretty content-heavy chapter, so we'll be splitting it between weeks 3 and 4. There's a lot of info within chapter 31 that we aren't necessarily going to be covering in detail for the purpose of this course, but make sure you're paying attention to the instructions inside of the module. There will be pages you can skip in the book listed there. We're going to start with processing domains, though. Let's review quickly the steps to digitizing the image. The patient data is going to be scanned, then sampled, then quantization occurs that allows for analog to digital conversion. Please review last week's videos if you might need a more thorough refresher. Then the image gets displayed on the monitor for use. Here's also several terms you'll need to be familiar with as we move ahead this week. Make sure you're doing the workbook to help you retain this info. Your assignments will contain info from the workbook, and all of the workbook answers can be found in chapter 31 of your textbooks. Again, this slide is review, so I'm going to skip this one and jump right to the next one. All right, so let's talk about image domains. What are they? Digital image information can be broken down into different domains. There are 3 image domains. And the spatial domain is primarily what we've been talking about so far in this course. We're most familiar with the spatial domain in digital radiography. In this domain, the matrix is comprised of numerical values representing grayscale. The intensity domain is a different way of evaluating a digital image that radiographers are typically familiar with. A histogram, which is a graphical representation of the numerical pixel values in the image, provides information about grayscale of your image. It often shows up on the control panel. The frequency domain isn't one that we typically use as technologists, but it demonstrates the size of the object in the image. Let's look at each of these individually. The spatial domain, we can look at the matrix. Here we're concerned with the specific location of each pixel within the matrix. Individual pixels can be located by identifying rows and columns they're associated with. Think of a grid structure in games like Bingo or Battleship. There are 3 operations that can be performed under spatial domain processing. There's point processing, which just means the software is performing a pixel by pixel or a point by point change to the pixel values, depending on the processing algorithm selected. Remember, an algorithm is just a set of instructions for the data, once it's captured, to be manipulated. For example, each body part and projection you have options for selecting have algorithms associated with them to tell the computer how to display the image. So if I select PA chest X-ray at the console and perform a PA chest view, that assigned algorithm expects pixel values to reflect the high subject contrast and adjust the image to look a certain way based on the preference of whoever designed the algorithm. However, if you perform that same PA chest X-ray using the same technical factors at the console, but you select the PA hand algorithm, the image would look much different. The hand algorithm, or any orthopedic algorithm, is going to be designed to be high contrast, to place emphasis on bony detail and not necessarily lung tissue. Selection of the appropriate body part and projection at the control panel assigns the algorithm you need for the appropriate appearance of the finished radiograph. Subtraction is another example that you might see in IR or if you've ever done vascular work in the OR. You just need to be able to identify what domain something falls under if I say point processing. Area processing focuses on a group of pixels. Not the entire image, but a specific section. The zoom function doesn't magnify the whole image, just a small portion of it, or a very specific area within the spatial domain. Global processing executes a function across the entire image matrix. So every pixel is affected. When you do a horizontal flip from left to right, you're affecting every single pixel. So that's a great example of global processing that occurs within the spatial domain. Intensity domain refers to the generation of a histogram. This will be covered more in detail next semester, but we'll just kind of skim the surface now. The intensity domain relates to specific pixel values referring to their gray level, stored in each pixel, regardless of their location on the image. In the histogram itself, the x-axis refers to the specific shade of gray, meaning are they light or are they dark? The y-axis, or the vertical axis, represents the number of pixels representing each shade of gray. An anatomical lookup table is part of the processing algorithm that gets applied to your image data. To take the chest X-ray algorithm example, the lookup table is a sample of what a histogram for a good chest X-ray looks like, and the software will adjust the actual image to appear similar to the lookup table's distribution of values in the histogram. That's why the pixel values change if you process your PA chest as a PA hand, because the software is going to distribute your pixel values similar to a good PA hand with that scale of contrast instead of the actual anatomy you exposed. And you can see the difference with the chest phantom here in the lab, processed as a PA chest on the left, compared to a little bit higher contrast image on the right using the PA hand algorithm. Same technical factors. A lookup table is basically just a sample histogram showing the computer what kind of histogram shape your actual radiograph is going to produce. We'll discuss more on this next semester as well, but I'll take a quick tangent back in time for some context here. Back in the film screen days, we didn't have to consider processing algorithm. The only control we had was the type of film and cassettes we were using, along with our KVP and mass values. When we first switched to CR, we didn't know why we were sometimes using optimal technical factors that worked for film, but the images weren't coming out like we needed them to. The sales reps from the vendors like Fuji and Kodak, now called Carestream, didn't know how to guide us at the time, but what some did as a workaround is change the processing algorithm after the fact. For example, you shoot a swimmer's view and you can't see the C7T1 junction, but you know your technical factors and positioning are fine. Some techs would just change the processing algorithm from a C-spine to a cross-table hip, and that was enough to change the image. It applied a different lookup table that worked well with that particular anatomy and allowed us to visualize the junction. There were big problems with this approach, though. Please do not do this. First of all, changing the algorithm post-processing will remove raw data from the image set before you send it to PACS. So there's limited ability to view more anatomical detail when you do this. It's why we don't want you to window level at your workstation before sending it to PACS. Also, your radiographs are legal documents. So imagine a hypothetical situation here. Your patient sues the hospital and surgeon for malpractice due to complications from their cervical spine surgery. When your beautiful-looking swimmer's view gets displayed as evidence in court, they question your competence because the information in the DICOM header shows you processed it as a hip. And they ask if you know the difference between a hip and a spine. All images should be appropriately signed in algorithm per the anatomy that you're x-raying. Changing the algorithm was a short-term band-aid fix, but the vendor could just come out and copy the cross-table hip algorithm, including the lookup table, and set it as the new swimmer's algorithm as a permanent solution, something they need to do. The tech can't do that. So an important thing to remember is when you window level, changing the brightness and contrast, you're changing the intensity domain functions. We always want to reset it before sending it to the radiologist. All right, off my tangent. Frequency domain relates to the size of the object being imaged, and similarly to the intensity domain, it also occurs regardless of location. Edge enhancement and smoothing are great examples of a frequency domain function. Fourier transform and inverse Fourier transform convert from a spatial domain to a frequency domain. This is typically used by physicists and engineers as a preference for looking at image data. All right, what does all this really mean? Why do we care? There's three approaches to sorting or processing any digital image. Sorting by location in the spatial domain results in a matrix. Here you can magnify and zoom in, which results in distortion of the image. Sorting by pixel intensity or grayness level, which changes the brightness and contrast. Or you can sort by object size, which results in frequency distribution, and this also influences detail or resolution. The main takeaway is to understand that each sorting or processing approach correlates to different features that allow you to manipulate the final image. These all factor into attributes of the final image, such as exposure or brightness, contrast, resolution, and distortion. We'll end this presentation here and pick up on histograms next time.